Hello everyone. So welcome to the video lectures on image and speech processing. So basically this course is about can be divided on like image processing and speech processing. So we will learn about few of the image processing techniques and later on we will deal with the speech processing techniques, like how is the speech processed. In the image processing part we will be talking about like what is the fundamentals of image processing, then the basics of image processing, then transform image transforms, compression techniques, image enhancement techniques. So we will be dealing with these topics in image processing. In speech processing we'll be talking about like what is speech, how can speech produced in humans, how is speech can be modeled in using digital signal processing concepts, right? So that will be dealt in the later part of the videos. So we'll be first in few videos we'll be talking about the image processing, right? So in today's topic we'll be starting with the introduction to the image processing. So what actually is image processing? Why do we require image processing? Where do you find these applications? So we'll be dealing with all those things, right? So what actually is the digital image processing? Okay, what is image processing? Why do we go for digital images? And what actually is digital image processing? So if we see in a very daily routine, we see everything as a picture. A human eye captures the every object in the form of a image, right? So that image is being processed by your brain, and you have your predefined data. Your brain is trained in such a way, saying that this is a pen, this is a laptop, this is a phone. So based on that, it is being it will get generated. Your brain sends request. So if we want to represent the same image what is captured in the real time, the using mathematical concepts, you can say that it is a two-dimensional function, okay, which is represented in the mathematical form as f of x comma y, where x and y are called as the spatial coordinate system. Okay, so what is the spatial coordinate system? In the mathematical form we have the xy axis, right? So this is like y axis, this is the x axis. So we have x and y axis are coordinate system. So similarly we can represent an image in the form of a two-dimensional image where x and y are called as spatial coordinates, and that defines the position of the point where we want to access, or where the processing is applied. Okay, now if we are saying that it is a two-dimensional function, we will also have an amplitude of that function. What is that amplitude? It is called as the intensity. So basically an image, in a layman term we say that the intensity of the screen is bright. It is like the screen is very bright. The For a laptop we say that, or we say that the sunlight is very bright, we are not able to see properly. So that here we are calling it to be an intensity, and that is being represented by the amplitude of the function, right? So when the intensity values x and y values are finite values, usually what will happen is a human eye captures an analog image. It is like there's a continuous image, right? So if such image is being considered for image processing in using your laptops or your computers, what happens is it takes infinite time. So what are we trying to do? We are going to use this x and y values to be a finite value. So such image is called as your digital image. So what happens is, if my x and y coordinate system, it is a finite and the amplitude is a finite quantity, then such an image we call it to be a digital image. So a digital image is composed of finite number of elements, each of which has a particular location and value. Since it is a finite value, it will have specific location as well as the value. Okay, these elements, okay, are called as the picture elements, image elements, pels, or most commonly called as pixels. Usually say that in our phone cameras we say that our front camera is of 13 megapixels, right? So what does that mean is, if an image is there, the minimum pixels, the minimum unit, square unit that can be defined by a camera is called as the pixels, right? So that is why We are also trying to define it here also. So the smallest unit of the image that can be represented using f of x comma y is called as the pixels. Okay, what is the digital image processing? Refers to processing digital image by the means of a computer. So what is a digital image? A digital image is a image which is having finite quantity of x and y as well as intensity values. So those intensity values, when they are processed using a computer, we call it to be a digital image processing technique, right? So what are the fundamental steps that are existing in a image processing is, if this knowledge base or other time otherwise called as the computer, then what actually do we have is, we will have the first step to be an image acquisition. We have to capture the image, like you have in different terms, like human eye is capturing the image, right? You have your ultrasound, you have your x-rays, so everywhere we are say having a sensor which is capturing the image. That image is shown in the form of your digital image in your in your screens of your laptop, your mobile phones, everywhere. So that, using some image filtering and enhancement techniques, we are trying to enhance the quality of the image. Say suppose it is in our we have in our mobile phones, you have different filters where it is like enhanced, it is where it is brightened. So those techniques are called as the image enhancement techniques. So image filtering is basically used to remove noise, and if you want a specific part of there also, you can use your image filter. Okay, if an image while transferring, so from a person to another person, if you are trying to transfer, we will have the effect of noise. So such images should be restored, right? So where there we will be using the image restoration part. The other part is like, before in our previous cases, we had a binary or a gray image. We all know that if we are considering a gray image, it will have the values from 0 to 255, right? Okay, if it is a color image, then it will have your RGB planes. Okay, how it is, what is it, we will see in the later part of the videos. Okay, now, so if an image is represented in the form of an RGB, then it is called as a color image. Okay, now a human eye can detect 6 million types of colors, whereas a human eye can capture or can differentiate only 24 shades of gray. So the thing is, like previously, because of lack of computers, lack of technology, a human we used to use only binary as well as gray images, but actually a human can differentiate only 24 shades of gray, like black, white, gray, dark gray, light gray, so on and so forth. So he can differentiate only 24. But the same eye, human eye, can differentiate 66 million color shades of color. So that is why we are going for color image processing, so that it is easy for us to differentiate and do the image processing techniques. Like we have wavelets and image transform techniques. Like what are the image transforms? Why are we going for frequency domain? All that we will have, right? And what the other concept is, like image compression. Image compression is basically what is the amount of space that is available, how much can we reduce the size of the image so that it is useful for us. So all those concepts, like morphological problem, segmentation, feature extraction, image pattern classification, these all are used for object detection using artificial intelligence. So these are the topics where are mostly used in artificial intelligence, right? Where you have to detect whether in your automobile case, if a traffic is more, traffic is less, based on the front traffic, so how many vehicles are there. So all that can be done using these techniques: segmentation, feature extraction, pattern classification, and morphological. Morphological processing is basically used for your biometrics. So all these are the digital image processing techniques. So based on the application, we can stop till whence. But the most common point is the image acquisition, right? So before we go for what is sampling and quantization, as I said, a human eye is actually an analog signal. Okay, if we talk in electronics terms, electronics and signals processing terms, then we can say that an image is always an analog. A human eye will capture it as in the form of an analog image. But when we go for computers, we have to convert into a digital image. That means we have to make the XY coordinate system to be finite and the amplitude of the function to be also finite. Right, so what is happening here is we have to make this xy and my coordinate systems xy as well as the amplitude to be finite. So the process of converting these into a finite, the analog to the digital image is done using my image sampling and quantization. Right, so if there are numerous ways to acquire images, we our objective is to generate an image, digital image from the sensed data. Right? There are numerous ways. You can through an X-ray, you can satellite images. You have different ways. Sound, X-rays, light, sonar. So you have different ways by which an image can be captured. But the main motto is this: from the sensed data, you have to generate a digital image. Okay, the output of the most sensors is a continuous voltage form whose amplitude and the spatial behavior are related to the physical phenomena being sensed. For example, what does this mean is like you have light, okay, you have sound. In your submarines, if you have submarines, you will pass through a sound wave. Okay, it will go and reflect the sound wave. This, say suppose this is the first ship and this is the second ship, it will send a sound wave. It goes forward till it reaches the obstacle. After it reaches, it comes back, it reflects back. So based on this reflected wave, it will try to create an image, right, of this ship, of this other ship. What is the size of the other ship, how much distance is that, all that can be calculated. So a sound is used here. You have your ultrasounds, baby scans, right, medical fields, you have x-rays, mris, all those are different forms by which the light as images form there. And all the sensors whatever are there, they generate a continuous voltage waveform. Right, so to create this image, we have to convert this continuous sensed data into digital format. That is, we are converting this analog image using this xy and fine amplitude to be finite. So these two processes are called as the sampling and quantization. Right, so how is this converted means it is done by sampling and quantization. So what actually is sampling, or what is this means? If I consider an example of this image here, okay, this is an example of the image. So what is this? If you try to capture, or if you try to plot a graph which is showing the sensed data, it will be of this form. What is this? From A to B. I'm just considering this line here. Okay, only a one sensed line. So what is happening here is it will be a continuous waveform, a continuous signal. Then it will drop because there is a difference in the intensity values, which is white and black. So it will drop. Then slowly it will be increasing and it will be constant again. Right. So you will see here this, whichever you are finding it to be zigzag here, this is called as the continuous intensity value. Right, so this is called as your uh, analog image. This is your analog image. So what are you trying to do is, we are trying to choose, or we are trying to convert into a sampled signal, sampled and quantized signal. So what actually is sampling is, we have an image like this. Okay, we are choosing some of the samples in this image so that we can reconstruct back our original image. Okay, so how are we choosing those pixels? Means you have, say suppose this pixel, other pixel, other pixel, like this. Say suppose I have, say suppose, so many number of pixels. Now what is happening is, I choose a pixel here, choose a pixel here, choose a pixel here, choose a pixel here, choose a pixel here. Using these pixels, I'll try to reconstruct back my original image. This is called as sampling. So what is happening is, sampling is done along the xy coordinate system. Okay, so basically if we have the number of pixels, various number of pixels, we are choosing only some part of my pixels. Okay, if we have, say, suppose 32 cross 32 image, so in that I'm choosing only the alternate pixels. So I'll have only 16 pixels among one column, right? So one row, right? So the choosing of number of pixels is called as samples. So what is happening here is, instead of having my continuous pixels, what am I doing? I'm choosing only few of the pixels. This is why we are saying that XY is becoming finite. So if I consider this analog image here, using here, what am I saying this? I'm choosing only few samples. This choosing, I'm saying it to be samples. So this is the samples at which I am choosing pixels. Okay, only these pixels I am using to reconstruct back my original image. So this is called as my sampling. So okay, now at what, this is my first pixel, this is my second pixel. What should be the distance between my first pixel and my next pixel? It is given by the Nyquist rate. It is given by the Nyquist rate. Okay, so based on the Nyquist rate, we will define what is the distance between first pixel and my second pixel, right? So what is the Nyquist rate is, the sampling frequency should be greater than or equal to f by 2. Okay, that means, just, okay, if my sampling time distance should be at least half of the, should be greater than or equal to the half of the, should be less than or equal to the half of the original time period. Say suppose I have an image like this. Okay, this is the time period. So what should be the, if I'm choosing a samples here, the distance between one sample to the other sample should be very much less than the half of the half of the time period. So if this is the time period t, then the distance between these two samples, which is, I'm saying it to be ts should be far less than t by 2, right? So this, if I'm talking in terms of frequency, that I can say it to be this, right? So this condition is called as the Nyquist rate. Now the next part, or the next is here is, what I were trying to do, the coordinate systems I have converted into digital, which is called as my sampling, right? Now after choosing this my samples here, I am considering what is the intensity values. Okay, now what am I doing is, I am converting this intensity values into discrete levels. Okay, I'm converting this into a discrete levels. That conversion is called as quantization. So how am I doing this quantization is, let me just erase this here. So how am I doing this quantization is, say suppose I have the intensity values from 0 to 255. Okay, what am I doing is, I am dividing it into subgroups here. This 0 to 255, I'm dividing into subgroups. Okay, say suppose this is 10, 20, 30, so on. This is like 250. Okay, this is actually 260, and here is the 255. So if we consider a gray image, all my intensity values fall between 0 to 255, right? So now what is happening is, I am saying that all the intensity values which are falling between 0 to 10, I am representing it by some single digit 0. Or say suppose this is 0th group, then 0 to 20, I'm saying it is represented by 1 by 2, like another group, subgroup as 1. So what I'm saying is, all the intensity values which are between 0 to 10 will be having a single value, which is, say suppose we'll take the middle value, which is 5. Okay, so what is this? All the intensity values which are between 0 to 10 will be termed as 5. So all will get converted. So what is happening here is, you will have only finite number of intensity values. Here you have 5, here you will have 50, here you will have say 25, so on and so forth. So you will have finite number of intensity, you have finite number of samples here. So you replace it, replicating that, when you are talking about intensity form, you will have your finite values of amplitude, which is like done using your quantization. So the same signal which is sampled here, when you do your quantization, you will see that all these values are of same value. So those are the quantized values. So these are the quantized values here. Now if we see clearly, this here, a curved part, whatever we had here, this curved part now changes to a trapezoid form. So how did we achieve this? All these intensity values, they are grouped to be one value here. One value which is of some intensity value. This group is termed to be another intensity value. This group, so on and so forth. So when we plot the intensity of this form, we will have my quantized waveform or the quantized image. Right? So using those sampling and the quantized values, if we try to reconstruct back, I get my image of this form. Okay, this is an analog form, this is the digital form where you can differentiate the pixels and the edges, right? So this is a continuous waveform, you have a smooth edge, but here you will have a you will have some error that we can call it to be a quantization error, right? So this is how you convert a continuous image to a digital image using sampling and quantization, right? Now the basic thing is like, how do you represent an image? We have converted into a digital image, but how is the image represented? So how is the image represented? It is represented in the form of a 2D function, a 3D function. Okay, this is where you are saying the xy coordinate system, which is giving the spatial coordinate system, and z axis, which is giving your amplitude. So this is the 3D represented. If you're trying to plot the only 2D plot, then you will have your 2D representation to be of this sort. The same thing, if you want to represent in the form of a numericals, zeros, 1, 2, 3 numericals, integers and all, then we will use the form of a matrix, right? So f of x comma y is equal to, you have say suppose m cross n size. Then what does this mean is the image is of m cross n size. That means there are m cross n number of pixels. So here in matrix we say that this is the first row, first column, right? So similarly, this position refers to the pixels position here. So how is that said is, if in almost all cases in image processing we consider this point, which is the leftmost corner point, top corner point, we consider it to be origin. So if f comma 0 comma 0, that means it is the 0th position. So this is the origin point will be given as the f of 0 comma 0. Then next we have f of 0 comma 1. Then this is the next pixel. Okay, this coordinate system 0 comma 1 is can be represented in the form of the rowth position and the column position in the matrix form. The values in the matrix will define the intensity value, which is also the amplitude value. So if I have an image, it can be represented in the form of x comma y. X and y is the spatial coordinate system that is defining the position of the pixels, and the amplitude of this function is defining the intensity value, right? So this is giving me the intensity value. So using these coordinate system and intensity value, I am representing the image in the form of a matrix form, right? So we have a 3D function, we can represent in this form. If you want to go for 2D functions, you go for this form. And if we have this matrix representation, which can be represented in this form, which in generalized form is represented in this form, right? Okay. So what is this image digitalization? Requires the decisions to be made regarding the values of m and the number of discrete intensity values, right? So if we are representing the image in the digital form, matrix form, we need to define what is the number of pixels that are there, which is given by m cross n, and the number of discrete levels that we have. Okay, there are no restrictions on the number of pixels that are required. The only thing it is like, it should be a positive integers values. Okay, if there are n intensity levels, then we say that L is equal to 2 per k, where k is an integer. This is defined by my quantization. This is also called as the quantization levels. Okay, number of quantization levels. This is also called as the quantization level. The dynamic range can be established by using the lowest and the highest levels of a system, right? Using my highest and lowest intensity levels, based on that we can define the number of levels. Okay. Now, what is the other term important is the image contrast. Okay, it is defined as a difference between the highest and the lowest intensity values. Okay, what do you mean by it is a high contrast image, it is a low contrast image? Means the difference between my highest and my lowest intensity values is very small. If it is of that sort, we say that it is a low contrast. If it is like large difference, we say that it is a high contrast image, right? Say suppose now I have L is equal to 2 power k, then that means that the number of bits that are required to represent or store an image is equal to m cross n cross l. So b is equal to the number of bits, then m cross n, which is the number of pixels, into k. So k is the number of levels that are from there. We get the value of k. So based on that, we have the number of bits, right? So another important thing is like when we go for interpolation. What do you mean by image interpolation? Is when you're trying to zoom or you're trying to shrink, rotate, or geometrically correcting the images, digital images, interpolation is used. So what is the interpolation means? Say suppose I have an image of 500 cross 500 image that we are trying to increase it to 750 cross 750. So what are we trying to do? We are trying to increase. So we have to, the main motto here is every pixel is having an additional pixel is introduced in between. So we know now the position of this extra pixel. We have to know what is the amplitude of this extra pixel. So we have to know its position as well as the amplitude of the newly introduced pixel. So what we say, extra pixel intensity values are to be calculated, right? So for interpolation. So how can it be done? It can be done by three ways, which is given by the nearest neighbor interpolation, bilinear interpolation, and bicubic interpolation. So what are these steps is, if it is a nearest neighbor interpolation, we are selecting the nearest pixel value and we are giving its intensity. Say suppose the nearest intensity value is having the intensity value 1, then the interpolated pixel will also have the intensity value 1. What will happen is, this is most easiest way, but what will happen here is it will distort a straight line. Okay, if you distort a straight line means, if you have a straight line here, if another break here it is happening and I'm trying to do this, so what is this here? At this point I will have an error. So the distortion in straight lines can be upset. Okay, what do you mean by bilinear? Because of this reason we are going for bilinear. So what do you mean by bilinear is, we select neighbors instead of using the nearest pixel here. Instead of using an only single pixel, nearest pixel, we are considering the nearest neighbors. Okay, we can use 4. Most commonly used is 4. We can also go for 8. Okay, so we are using the 4 nearest neighbors and we are trying to estimate the intensity value. What is the advantages? It gives better results than the nearest neighbor, better results than the near. But an interpolation is done, because of which, I mean, like we are considering the 4 neighbors and we are trying to do, so what is happening is computational burden is increasing. But whereas when we go for bicubic interpolation, we are using the 16 neighbors. Here also the advantage is it gives you better than the bilinear, but computational burden also still exists. So most usually we use 4 neighbors or 8 neighbors. So using these three techniques, we can try to find out the interpolated pixel position as well as my amplitude value, right? So we have talked about the pixel values, right? So neighbors in the interpolation part, we have talked about my neighbors, right? What actually is my neighbors? Say suppose I have a 3 cross 3 pixel segment. I have taken a 3 cross 3 image segment. Okay, now if I consider here the center point is my pixel of my interest. Now what happens here is, I have a pixel above and a pixel below. I have a pixel to my left and pixel to my right. Okay, these four are called as my horizontal and vertical neighbors. They can also be called as my four neighbors. Okay, so these are called as my 4 neighbors. The pixels which are at my diagonal position, they are called as the diagonal elements, which are represented by ND. The whole combinedly with 3 by 3 image here, which are having the diagonal image as well as my 4 neighbors combinedly, is called as the 8 neighbors. Right? So for a pixel, I will have both diagonal neighbors, 4 neighbors, as well as my 8 neighbors. Diagonal elements plus the 4 neighbors combinedly is called as my 8 neighbors. Right? So the next part of this thing, based on my neighbors, is called as the adjacency. Okay, now in usual thing we can say that the point here and these 2 points are adjacent. Same example, 1 and 2 are adjacent numbers, right? So similar way, these things I cannot apply for my image processing. The For image, for 2 pixel values to be adjacent to each other, there are conditions to be satisfied. Okay, what are those conditions? Is they have to be, first condition is they have to be neighbors, and second condition is they have to be in the same V set. Okay, the pixels, 2 pixels are neighbors to each other, as well as they are having the same gray levels or the binary values, and they are in the same set adjacent values, then we are terming it to be a adjacent pixels. Right? So what is happening here is, let me just consider an example here. Okay, I am considering that by binary image, right? So binary image means I will have a V set, or the possible number of intensity values to be 0 and 1. So I'm considering 2 subsets here. Okay, one subset is 0, the other subset is 1. Right? Now, if a pixel is having the intensity 1 and another pixel is having 0. Okay, now let's consider this pixel. Okay, I'll consider this pixel. Now, what are my 4 neighbors? This is my 4 neighbor, this is my 4 neighbor, this is my 4 neighbor, this is my 4 neighbors. Now, if I want to consider the adjacency, what is the first thing? Neighbors. Neighbors, yes, all these 4 are neighbors. So first condition is satisfied. I have to consider now they should be in the same subset, right? So what is the same? V set, which is the subset of my total number of possible intensity values, right? So if we observe here, 0 and 1 are in 2 different subsets, right? So if I see clearly, these 2 points are having the value 0, right? So they belong to the same subset. Whereas when I come for 0 to this here, they are also in the same subset. The same thing when I go for here and as well as here. 0 1 0 1, they are, the intensity values are in the 2 different subsets. So these 2 terms, which is like 1 here, and this one, they are not adjacent. But this 0 as well as this 0, they are adjacent to each other, right? So they are the adjacent to each other. So if you see clearly here, both 0 and 1, it is a binary image, we have zeros and ones, right? So the intensity values can be 0 or 1. So 0 is one subset, 1 is the other subset. So if they are in neighbors as well as in the same subset of the V, then we can say it to be adjacent to each other, right? So similarly, if we go for a gray image, and I'm saying that my V set is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, now if I consider here this pixel, I'm considering my pixel 2. What are my 4 neighbors? This, here, 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 and here, right? Now if I see clearly here, 100, 150, 34, they are not in the same V set. So they cannot be adjacent pixels. Whereas when we come for 3, they are adjacent pixels because they are in the same set. Okay, now let's go for the 8 neighbors. I have 10, 9, 45, 200. These are the diagonal neighbors. So combinedly we have the this. Now here 10, 10, 8, they are in the same subset, right? So you will have your adjacent. So 2 is adjacent to 10, adjacent to 8, adjacent to 3. Whereas it comes for 245, they are not in the same subset. So this is called as the adjacency, right? Here, in this example, 2 and 3 are related by 4 neighbors. They are related by 4 neighbors. So such adjacency which is created by 4 neighbors is called as 4 adjacency. Okay. 2 and 8 are related by 8 neighbors. There are 8 neighbors, right? So this is called as my 8 adjacency. Okay. We have another term called as the mixed adjacency, which is given by if you have both 4 and 8, then we call it to be a mixed adjacency. So let me give you an example for clear understanding. So if I see here, I have a 1 here, I have a 1 here, 1 here, 1. Right? So what is happening here is 1 and 1, they are related by 4 neighbors. This is related by 8 neighbors. I can say this one is related to here this one by using this correlation. Right? So this is 4 neighbor, this is the 4 neighbor. Right? So a pixel here, this pixel and this pixel can be related by 8 neighbors directly, or it can be related by 4 neighbors in this form. Okay, so such type of adjacency, if it exists, it is called as the 8 adjacent to each other. It is called as the M adjacency, which is the mixed adjacency. Okay, so if a mixed adjacency is existing, we give priority to 4 adjacency. Okay, we give priority to adjacency 4. So we say that, let me just erase it a little here. So we say that this one and this 1 are related by 4 adjacency instead of mixed 4 adjacency. We say it to be a mixed 4 adjacency. Right? So this is how adjacency and neighbors are related, right? So this is the uh, reference book, Gonzalez books, from where you can read about more about pixels relations, which are adjacency and neighbors. So rest of the discussion will continue in the next video. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.